What if I told you that one of the most impressive performance stories in automotive history didn't involve a big engine, insane horsepower, or speed records? In the 1950s, while manufacturers were obsessed with numbers, a small Swedish car with barely 60 horsepower was quietly doing the impossible. It was outlasting, outperforming, and surviving cars that were faster, more powerful, and far more expensive on paper. This wasn't a concept car or a marketing stunt. It was a real production vehicle, built for real roads, in one of the harshest environments on Earth. Snow-covered highways, sub-zero temperatures, endless miles where mechanical failure wasn't an option. And under those conditions, where raw numbers stopped mattering, this car completely rewrote the definition of performance. Because real performance isn't about how fast a car can go for a few seconds. It's about how long it can keep going when everything is working against it. Today, performance is almost always reduced to numbers. Horsepower dominates advertisements, 0 to 60 times are repeated endlessly, and specification sheets are treated like final judgment. The message is simple: more power means better performance, and better performance means a better car. That belief has shaped the automotive industry for decades. It influences design decisions, consumer expectations, and even how success is measured. But numbers have never told the full story. Some of the most important engineering lessons didn't come from record-breaking speed runs. They came from real-world conditions where theory failed and reliability mattered more than reputation. To understand that lesson, we need to go back to a time when limitations were unavoidable and cars were built for survival, not status. It was 1956. Europe was still rebuilding after the devastation of World War II. Infrastructure was damaged, roads were inconsistent, and vehicles were purchased out of necessity rather than comfort. Fuel quality varied widely between regions, and mechanical reliability could never be assumed. In many parts of Europe, especially in the north, owning a car was not about status. It was about survival. In Sweden, this reality was impossible to ignore. Winters were long, dark, and unforgiving. Temperatures regularly dropped far below freezing, roads remained covered in snow and ice for months, and distances between towns were vast. A breakdown in these conditions was not just inconvenient. It could be dangerous, even life-threatening. Under these circumstances, reliability was not a selling point or a marketing term. It was the single most important requirement. A car needed to start every morning, operate consistently for hours, and continue functioning even when conditions were far from ideal. It was during this period that a Swedish engineer presented an idea that many considered unrealistic. He claimed that a car producing just 60 horsepower could outperform vehicles that were significantly more powerful, more complex, and far more expensive. On paper, the claim made no sense. At the time, automotive progress was measured almost entirely by output. Bigger engines were assumed to be better engines. Advanced mechanical systems were believed to guarantee superior performance. To most engineers and executives, the idea sounded outdated before it was even tested. Performance without power felt like a contradiction. A vehicle that failed to impress on a specification sheet was assumed to be inferior by default. But this was not a marketing stunt or an attempt to provoke attention. It was the result of deliberate engineering logic. Instead of increasing horsepower, the engineer focused on efficiency. Instead of designing for brief moments of peak performance, the goal became sustained performance over long distances. The car was engineered for real roads, real drivers, and real conditions, not perfect test tracks or controlled environments. Every component was designed to operate consistently under stress rather than briefly under ideal circumstances. The engine was intentionally modest. Lower output meant reduced heat, lower internal stress, and improved longevity. Components were kept well within safe operating limits instead of being pushed to their extremes. This approach dramatically reduced the likelihood of failure. Thermal loads remained stable, were accumulated slowly and predictably. The result was an engine that could run for hours without overheating or degrading in performance. The suspension system followed the same philosophy. While more advanced designs existed, rigid beam axles were chosen for their durability and predictable behavior. They tolerated rough road surfaces, maintained alignment under heavy load, and resisted damage in conditions that challenged more complex systems. Materials were selected for endurance rather than weight savings. Cooling systems were deliberately oversized to ensure stable operating temperatures during continuous operation. The vehicle was not built to impress during a short test drive. It was built to perform reliably over thousands of kilometers with minimal intervention. When testing began, expectations were low. Competing vehicles arrived with larger engines, more advanced suspensions, and superior specifications on paper. At first, they seemed to confirm conventional thinking. The high-powered vehicles accelerated faster and achieved higher top speeds. In short demonstrations and controlled scenarios, they appeared dominant. Observers saw exactly what they expected to see. More power produced more immediate performance. But as testing continued and distances increased, a different pattern emerged. Heat began to build inside high-output engines. Mechanical stress accumulated. Cooling systems that worked well during brief operation struggled under continuous load. Complex systems introduced additional points of failure. Small issues that were insignificant during short tests became serious problems over time. Minor leaks, alignment issues, and thermal inefficiencies slowly reduced performance. In some cases, they caused complete mechanical failure. Meanwhile, the modest Swedish car continued steadily. It did not dominate sprints or impress with speed. But where other vehicles stopped for repairs, it stopped only for fuel. Where others slowed down or dropped out, it continued operating exactly as designed. Engineers began to notice something important. Over long distances, consistency mattered more than peak capability. A car that maintained a moderate pace without interruption often covered more ground than one that was faster but unreliable. Performance, they realized, behaved very differently over time than it did in short demonstrations. Higher horsepower engines generated more heat, and that heat placed constant stress on internal components. As temperatures increased, efficiency dropped and wear accelerated. Cooling systems that were sufficient for brief use became overwhelmed during sustained operation. Mechanical complexity, once considered an advantage, became a liability. Advanced systems required precise tolerances and consistent maintenance, neither of which could be guaranteed in real-world conditions. Small failures accumulated, leading to reduced performance and frequent breakdowns. The Swedish car avoided these issues by design. Its engine produced less power, but it also generated far less heat and experienced significantly lower mechanical strain. Because components were not pushed to their limits, they remained stable even after hours of continuous operation. The suspension system played a critical role as well. Simpler designs absorbed rough surfaces without excessive wear. Predictable behavior reduced stress on both mechanical components and the driver. Weight distribution and balance were carefully considered. Instead of aggressive tuning, the vehicle was engineered for stability across a wide range of conditions. This reduced driver fatigue, improved control, and minimized the likelihood of mechanical stress. Fuel efficiency further reinforced this advantage. High-powered engines consumed fuel rapidly, requiring frequent stops and placing additional strain on supporting systems. The modest engine operated efficiently across a wide range of speeds, allowing the vehicle to travel farther between refueling stops. As results continued to accumulate, the contrast became impossible to ignore. Vehicles designed to excel under ideal conditions struggled to adapt to prolonged, real-world use. The Swedish car, built specifically for those conditions, performed exactly as intended. It did not dominate any single metric. Instead, it consistently met performance requirements across every scenario. This forced engineers to reconsider long-standing assumptions. The belief that more power automatically meant better performance was no longer supported by evidence. The testing revealed a critical truth: reliability is not separate from performance. It is a core part of it. A car that fails cannot perform, regardless of how impressive its specifications may appear. A car that continues operating reliably maintains effectiveness even if its numbers seem modest. Attention gradually shifted away from raw output and toward overall system design. Simplicity became a strategic advantage. Fewer components meant fewer failure points. Conservative engineering reduced uncertainty and improved predictability. By the end of testing, the results were clear. Over extended distances and harsh conditions, the modest Swedish car had proven itself competitive with, and in some cases superior to, vehicles with far greater power. True performance was not defined by peak numbers. It was defined by endurance. This realization marked an important shift in engineering thinking. It showed that performance could not be captured by specifications alone. Instead, it emerged from the balance between reliability, efficiency, and real-world usability. What initially appeared to be conservative engineering was now understood as deliberate restraint. Every design choice reduced stress, minimized uncertainty, and ensured predictable behavior over long periods of use. Over time, this philosophy influenced automotive design far beyond a single model. Scandinavian engineering became associated with durability, safety, and long-term reliability. Vehicles were built not to impress briefly, but to endure. The lesson remains relevant today. In modern gasoline cars, electric vehicles, and complex systems of every kind, sustained performance matters more than peak output. Efficiency, thermal management, and reliability continue to define real-world success. True engineering excellence is often quiet. It does not announce itself with extreme numbers or dramatic demonstrations. It reveals itself over time, through consistency, trust, and the ability to perform again and again under real conditions. That is what real performance looks like.